Welcome to the final video tutorial for Learning Music Theory with Logic, Max, and Finale, published by Routledge and written by Jeffrey Kidda. In this video tutorial, we'll discuss the contents of the last chapter, which is entitled Sound and Music Theory. We'll discuss the concept of frequency. We will look at audio waveforms, including instrumental waveforms and synthesized waveforms. We'll talk about the overtone series and its relation to timbre. We'll discuss the concept of intervals with regard to frequency and how intervals and scales can be understood in terms of frequencies. We'll look at an example of a kind of tuning called just intonation and how we can create an A major scale with just intonation using a max patcher. We'll discuss the concept of intervals as frequency ratios and the implications of that for different tuning systems and temperaments, specifically looking at a generalized mean tone tuning system and the equal temperament system, which is used today. We'll end up by looking at a tool in Logic which allows us to explore different kinds of temperament systems. When we listen to a violin tone, we hear a pitch, and the pitch is based on what's called the fundamental frequency. The fundamental frequency is the number of cycles of the waveform per second. So every musical instrument that plays pitches has a frequency of the fundamental. We're looking at a violin tone of E4, which has a fundamental frequency of 330 hertz. With Logic, we can get a close-up image of the waveform, which is what we have here. And we can see that in the enclosed rectangular shape, we have one cycle of the waveform. If you see the rest of the waveform going from left to right, you'll see that that one cycle is repeated 4 times. When we're listening to the violin sound, it's going to be repeated 330 times per second when the note is sustained. This particular waveform has a number of ups and downs to it and is therefore a complex waveform. Instruments and voices produce complex waveforms, but with synthesizers and computers, we can produce simple waveforms such as sine waves, triangle waves, square waves, or sawtooth waves. Now we're zooming in on the waveform, and with the cursor we're seeing the beginning of each one of the cycles in this particular view, the cycles of the wave. The most simple of the simple waveforms is the sine wave. In the upper image, we see a sine wave, which in this case has the frequency of 440 hertz. Remember, that means that there are 440 cycles of the waveform every second. With Logic, we can also take another view of the sound, which is using Logic's EQ plugin in the analyzer mode. And this shows us that this particular sine wave has energy, has that peak, only at one frequency, which is 440 hertz. The sine tone's EQ image will remain constant, whereas when we look at the image of the EQ analyzer for instrument sounds or voices, it will be more complex, and it will also be more dynamic because it will show various frequencies that are shifting. First, the sine tone. The violin sound that we listen to looks like this in the EQ analyzer view. If we view it in real time, we'll see the energy amounts that are shifting above the fundamental frequency. The fundamental frequency here is again 330 hertz, and the upper frequencies that we see here are called the harmonics. The harmonics are whole number multiples of the fundamental frequency, 2 times, 3 times, 4 times, 5 times, etc. It's difficult to discern their numbers from this graph. The harmonic overtone series is based on whole number multiples of the fundamental frequency. So for a fundamental frequency of 330 Hertz, the harmonics will be 660, 990, 1320, 1650 Hertz. When we listened to the sine wave, we saw the graph form and we noted that it has energy only at the fundamental frequency. We can combine sine waves according to the harmonic overtone series to create other waveforms as well. For instance, square waves have odd-numbered harmonic overtones with decreasing energy for the higher overtones. Triangle waves have odd-numbered harmonic overtones, but with a greater slope of decreasing energy for the overtones. The sawtooth wave has both odd and even-numbered harmonic overtones with decreasing energy amounts. This max MSP patcher allows us to create sawtooth waves and square waves. We create the sawtooth wave by including all the harmonics, and we create the square wave by including only the odd harmonics. The combination of harmonics with a fundamental frequency is what allows instruments to have different timbres. So one way to understand timbre as relates to instruments is that each instrument combines the overtone series in different ways. As an example, the trumpet has a very rich number of overtones, and they're very bright sounding. They're very present. On the other hand, the flute has relatively fewer overtones that we hear in the flute sound, and thus you could say that the flute is closer to a sine tone than the trumpet, and the trumpet is closer to a sawtooth wave. We have identified intervals by ordinal number, that's to say seconds, thirds, fourths, etc., and quality, major, minor, diminished, or augmented. We've also identified intervals as being consonant or dissonant, melodic or harmonic, or as simple or compound. Intervals can also be identified by the ratio of their fundamental frequencies. The octaves' fundamental frequencies, for instance, are at a ratio of 2 to 1. So an octave above tuning note A4, which has a frequency of 440 Hertz, is A5, which has a frequency of 880 Hertz, fundamental frequency of 880 Hertz, and has an octave below at A3, which has a fundamental frequency of 220 Hertz. Intervals based on simple ratios are pure, and a system of tuning that relies on pure intervals is known as just intonation. In this chart, we have the notes of an A major scale based on just intonation intervals and simple ratios for the pitches above A220. Starting with A220, we have the A major scale, and for each of the notes of the scale, we will base the frequency, the fundamental frequency, on a simple ratio. For instance, a major second up from A, the B will be based on a 9:8 ratio, which means that we multiply the fundamental frequency by 1.125. The major third above the fundamental, or the A, will be based on a 5:4 ratio, and we'll multiply that lower frequency by 1.25. We can continue all the way through the scale till we get to the octave, which, as we mentioned before, is doubling the frequency. So we go from 220 hertz to 440 hertz, and we have all of the scale notes in between, all of the scale steps in between. We can create this just intonation A major scale with a max MSP patcher. When we listen to the scale, it sounds like an A major scale. However, some of the intervals produced are different. So for instance, considering the minor third between C sharp to E, this has a pure ratio of 6:5, or 1.2 multiple. It's a pure minor third. B to D is also a minor third, but based on this just intonation A major scale, the frequencies 245.5 and 293 hertz create a multiple of 1.19, which is obviously different from the 1.2 multiple in the minor third between C sharp and E. This is just one small example of the kind of discrepancies in intervals that just intonation will create. And therefore, it means that just intonation is not particularly useful for most musical situations. Another system of tuning is Pythagorean tuning. In Pythagorean tuning, we're basing everything on the idea of pure fifths, a ratio of 3:2, or a 1.5 multiple of a lower frequency. If we want to get all the pitches of the chromatic scale, we can ascend by perfect fifths. And for instance, starting at A0 or 27.5 hertz, we can get all the pitches but arranged in fifths, as in A, E, B, F sharp, C sharp, G sharp, D sharp, A sharp or B flat, F, C, G, D, and then back to A. If we ascend this way by pure perfect fifths, we will eventually get to another A, namely A7, starting from A0 and then getting to A7. With pure fifths, this A7 will be at 3,568 hertz. If we get to this pitch with octaves, and we'll remember that with octaves we double frequencies, however, the A7 will be 3,520 hertz. The two pitches are noticeably different, and the interval between them is the Pythagorean comma. The Pythagorean comma can also refer to other small intervals between enharmonic spellings. The difference between these two frequencies is 48 hertz, which is quite a noticeable difference. So Pythagorean tuning doesn't work all that well for musical systems, but starting in the 16th century, musicians developed other ways of creating tuning systems. Temperaments are tuning systems for musical use. Just intonation doesn't work as well in chromatic music, nor does the approaches we saw with Pythagorean tuning. So other temperaments were developed. Among the many historical temperaments was mean tone tuning, which exists in various forms. Mean tone tuning has a slightly smaller fifth than a pure fifth, and it seeks to create pure thirds. Mean tone tuning also works less well with chromatic music. Eventually, the equal temperament system was widely adopted. In equal temperament, the semitones are all the same size, but other intervals are not pure. They become not pure because the semitones are all the same size. The advantage is that all the keys sound equally absent of pure intervals. We can compare the sound of triads in the three tuning systems and a major triad, and we'll notice in particular that the major thirds sound quite different. And in particular that the just intonation major third is much more tranquil sounding as compared with equal temperament or the mean tone tuning system. Logic has a very powerful tool for exploring different temperament systems. We can change the temperament of the software instruments to various forms. And what is particularly interesting is to listen to two examples of music. Let's say a diatonic piece of music, perhaps from the early Baroque period, and then alternatively a piece with chromatic harmony. And if we listen to these with both historical tuning and with equal temperament, we'll see that the chromatic music suffers particularly with the early temperaments, whereas diatonic music can have a nice character with those early temperament systems as long as there aren't any chromatic notes or chords. Here's a list of Logic's historical tunings. And in the last example, we'll compare a piece by Purcell with a piece by Schubert. The Purcell is completely diatonic. The Schubert has applied dominance. Thanks for watching.